You are
I
muted.
cannot, we cannot hear
Gaurav,
you.
you are muted. Yeah.
Yes,
Can you hear me now?
Yeah. Yeah.
now we can hear you.
Yeah, hi. It gives me great pleasure to introduce Michael Schlosser. And he's going to, this is a really special seminar because he's going to present his 100th paper, which is called Bilateral Q Ultraspherical Functions. So over to you, Michael.
Okay, thank you very much for your very kind words, especially the first ones where you were muted. But okay, so that was the first joke. I'm not sure if there will be more jokes. Anyway, it's a pleasure for me to talk in your very nice seminar. My talk will be on a bilateral extension of the continuous Q-ultraspherical polynomials, which I call bilateral Q-ultraspherical functions. So, okay, yeah, so here is the outline. In order to describe the objects, I have to recall, and the ingredients, I have to recall a little bit of the theory of basic hypergeometric series. Then I will tell you what is the most important facts about the classical theory, that is about the continuous Q-ultraspherical polynomials. Those I will generalize to bilateral series in a way that they still form a full family of orthogonal functions. Now they are not polynomials anymore, so they do not terminate. They are non-terminating, and indeed in two ways. So they terminate, they're non-terminating. Well, they're true bilateral series. So while the polynomials could be considered to be series from 0 to n, they're from minus infinity to plus infinity. That's why I call them now functions. And I will explain you how orthogonality is established, and then I will just mention some other results. So also I will show you a few other results explicitly, like generating functions, maybe the action of the Esquivel-Wilson operator and things. But most other results I will just show, will just describe to keep it, yeah, maybe focused on the orthogonality and on the structure. Okay, and please interrupt me at any time if you have any questions. I will be happy to get feedback anyway, so that I know I'm not just talking against the screen, but yeah. So here's the of course the ingredients for the basic hypergeometric series, the Q-shifted factorials. I assume Q here to be a let's say a complex number between 0 and 1 in absolute value. The Q-shifted factorial is now conveniently defined as a quotient of two infinite products because I will need the k, the sub k here in the Q-shifted factorial aq sub k to be an arbitrary integer. So it will be positive or negative. If it's positive, this quotient will reduce to a product of k factors in the numerator, else we will have minus k factors in the denominator. Okay, this is all well known, of course, and this I'm just recalling this notation. And also I will use this important notation for, in the first case, for symmetric products, symmetric in plus theta and or e to the I theta and e to the minus I theta. They will frequently appear. So, or you can think of z being an extra variable denoting e to the I theta, so it's symmetric in z and 1 over z. And of course, I have this product notation, which is convenient. Okay, so this is should be familiar to the audience anyway. Then here's the unilateral, bilateral. First, the unilateral, not the bilateral, the unilateral basic hypergeometric series, where it's enough for me to consider such series where we have the same number of factors in the numerator as in the denominator. Because of the q in the denominator, the series naturally terminates from below. So we can also regard this as a series overall k in the set of integers z. And of course, z should be between 0 and 1 in absolute value for convergence. In the bilateral case, there's an extra condition needed for convergence, not just z less than 1, but also the product of the b's divided by the product of the a parameters, but divided by z, that should be less than 1 in absolute value. But anyway, that's also well known. The 1 psi 1 summation, which I will show you soon, has such a feature. So because there's no q here, which naturally makes the series terminate from below, this is a genuine or true bilateral series with r upper parameters, r lower parameters, base q, and argument z. Okay, uh, that is the notation. The Q binomial theorem is, of course, maybe the most famous Q-series summation, which can be written in terms of, convenient in terms of a basic hypergeometric series. So it's a general 1, phi 0 series with upper parameter A, base Q, and argument Z. And we assume always implicitly that Q is less than 1 in absolute value, that we need here for these infinite products to converge. And for the series to converge, we need that Z is less than 1 in absolute value. If this is not the case, we can, of course, we have analytic continuation, but then we do not have the series representation here. And yeah, but of course, the product side still converges even if Z is not less than 1 in absolute value. But then we have other representations, of course. But that is not the issue of today's talk. I just want to, the next step will be to show that this naturally extends, and then we can also ask questions about other things. So at first it extends to the bilateral case, and then we can ask similar questions about orthogonal polynomials if they also extend to bilateral series, and that is the direction I'm going to. So this classical identity, the 1 phi 0 series, has been independently discovered by Cauchy, Heine, and Gauss in about 1840s. And then Heine developed a theory of Q analogs of hypergeometric series, and systematically, and sometimes these are called Heine's hypergeometric series, but of course nowadays we just say Q or basic hypergeometric series. I might be too elementary here, but since the talk is being recorded, and maybe the talk should be also accessible to students, to graduate students, I think it does not hurt if I'm very elementary and make my talk quite accessible. So here's what I mentioned about the bilateral series. So the 1 psi 1 encodes in its notation, of course, the bilateral series. This is sum from minus infinity to plus infinity. In the 1 psi 1, we just have one upper parameter. We call it A, one lower parameter B, and the argument Z. These are the conditions of convergence. So Z is actually now not in a unit, in a disk, but in an annulus between b over a in absolute value and 1. And the right-hand side is very nicely just a product of q-shifted factorials. Even if it's in the denominator, I call it a product, of course, with negative multiplicity in a sense. But anyway, so you have here a very nice product, 4 q-shifted factorials in the numerator, 4 in the denominator. While here you have just 1 in the numerator, 1 in the denominator. So there are various proofs of the 1 psi 1 summation. Ramanujan never gave a proof of it. And this result was actually only published after his death, as far as I understand, by Hardy. in the memoirs to Ramanujan, essentially. And he attributed it to Ramanujan and said that this is a remarkable identity with many parameters. And yeah, he didn't explain anything about the use of this, but of course, this is a very important special function. And one of the first proofs was given by Wolfgang Hahn using functional equations. And then there were other proofs given. And a conceptually fundamental proof was given by Murat Ismail by analytic continuation. So not in Z, not by looking at seeing that this is a special function which is meromorphic in Z, or let's say analytic in an annulus in a certain region, but looking at it, viewing this as a function in B. So if B is Q, it's easy to see that this reduces immediately to the 1, phi 0 series. Of course, the region of analyticity can then be extended in that case, because the lower condition here is not necessary then. But anyway, it's a non-trivial region of convergence, and then we can just expand it to where it makes sense. But also, if B is of the form Q to the, let's say, S, where S is any non-negative integer, positive integer, sorry, then it corresponds to a shifted version of the Q binomial theorem here. And so the sum just doesn't start from 0, but then at minus S in that case. And we get another instance of the 1, phi 0, 0 series. And well, the Ismail argument says that if this function is analytic on the left-hand side in B, on the right-hand side it's analytic in B as well, and it agrees with, for the values B equals Q, Q squared, Q to the third, and so on, Q to the S for any S, and this sequence converges to 0, to a point which is in the domain of analyticity of B, then, okay, and that's the proof. So by the identity theorem, we have established this identity. So this is Murat Ismail's argument. And this argument I will use to extend the orthogonality relation of the continuous Q-spherical polynomials to that for the bilateral Q-spherical functions. That's why I'm explaining it in detail here. Okay, so there are, of course, more identities than these simple identities, which are useful in, let's say, the study of continuous Q-spherical polynomials. For instance, the Q-Gauss summation by Heine, the Q analog of the Gauss summation, the 2f1, the famous 2f1 summation. It's here. Okay, there is also for bilateral series, and that will be used in the study of the bilateral Q-spherical functions, the Q-Kummer summation. It's a well-poised series on the left-hand side. Not very well-poised, but well-poised. So B times AQ over B is AQ. The same C times AQ over C is AQ. So it's well-poised. And similarly, the Q-spherical functions, which you will see later, they are also well-poised series. Of course, they have a more general argument here that does not depend on AQ and BC, but on Z or on e to the I theta. But anyway, in special cases, we can see that we have an evaluation by the by this bilateral Q-Kummer summation. And of course, for those who are experts in the audience who know the 6x6 summation, there's a way to reduce to get rid of the very well-poised terms by letting D equals, well, and E suitably, and then you're just left with B and C, and you have a well-poised series, and that will be what. So that also explains somehow the quadratic nature you have here in this summation. Interestingly, what is also used in the study of bilateral Kyoto spherical functions will be Bailey's 3 psi 3 summations, which are here. They are they also come from the 6i6 summation, but in a different way, by symmetry in some sense. Anyway, so there are also not so many bilateral Q-series identities of known. And it's interesting that all of these appear in the study of bilateral Q-spherical functions. This is also an interesting feature of the theory of Q orthogonal polynomials, that there's a very strong relation to all kinds of identities and transformations for hypergeometric and Q hypergeometric series. And so in some way, it's natural to, if you have some identity, also to ask, is there any connection to orthogonality, possibly? And because there are these bilateral identities, one is, of course, tempted to ask, so are there bilateral series which are orthogonal? And that's what I'm showing you then. Okay, so here now, so the introduction, can I hear any person from you? Is everything fine? Can you hear me well?
All good.
Okay, then I can continue because I don't see anyone and I don't know if you can hear me. Yeah, okay. Okay, so these are the continuous Kyoto circle polynomials which I want to extend so that also the nice properties extend, of course. So I will show you the nice properties I'm interested in. So this is now a 2phi1. Okay, it's not written in basic hypergeometric complete base in a normalized basic hypergeometric form, but in a symmetric form where you see there's some symmetry here. If you replace uh, k by n minus k, you essentially have the same here, but then you see that this function is symmetric in theta and minus theta, or e to the I theta and e to the minus I theta. So it is in the space we're interested in. So such functions which are symmetric in e to the I theta and e to the minus I theta can be expanded in terms of cosine theta. Or you recall that cosine I theta is just e to the I theta plus e to the minus I theta over 2. So we can, this is a function in cosine theta, which we call x. And actually, this is a polynomial in x of degree n. And Rogers was the first to study these functions, but not from the point of view of orthogonality. He was not, I mean, he could have done that, but he was not, it seems he was not aware of their orthogonality, but he needed them in his approach to prove the Rogers-Ramanujan identities. So not just prove them, but to derive them. So he was actually the first to derive the Rogers-Ramanujan identities. And so he had some functional equations and so on, and then different operators, so kind of operator method and he, a very important ingredient was this continuous Quadratic polynomials. They satisfy nice properties. You will see the linearization formula then, for instance, which somehow explains that they decompose. Yeah, there's a kind of nice, maybe product formula for them, which somehow is implicit. And it was all in his construction of Rogers, in Rogers' work, and Rogers needed that linearization formula. So he was the first to discover that as well. Okay, so what is remarkable here, so there's not just an x, but also a beta. So without this beta, I think with beta equals 0, we have the Q-Hermit polynomials. And so these extend the Q-Hermit polynomials. And okay, here's the basic hypergeometric representation. So we pull out beta q to the n, q to the n, so everything which depends on n, and have this as a normalized series from 0 to n. And this will have this form, which is now less symmetric, but anyway, it's a 2v1. We also don't immediately see here that this is a polynomial in x of degree n, but believe me, it is. Also, this is actually symmetric in e to the I theta and e to the minus I theta due to one of Hanne's transformations. Uh, these satisfy a very nice generating function. So if you, okay, here's maybe the result. So if I just multiply Cn by t to the n and sum over all n, we have a nice closed form, which comes from here. So this is really decomposes nicely. So, okay, I will show you the proof in the bilateral case. From this generating function, one can very easily get the recursion formula and see that these satisfy a three-term recurrence relation. So this is recursion in n. So we multiply by x. Here the coefficients of Cn plus 1 and Cn minus 1 are independent of x, but they depend on the parameters beta and on n. But anyway, this is a type of forwards relation, and this shows that these are actually orthogonal polynomials. There are certain conditions on beta uh, needed to make it the weight in the orthogonality relation positive definite, but this is just a formal thing. For in generalized orthogonality, we don't need positivity. We're just interested maybe in orthogonality. That means that there's some kind of inner product which reduces to delta nm if we combine two different elements, Cn and Cm. But anyway, with positive definite, with certain conditions on beta, we have even orthogonality. And I will show you the relation soon. These are the two initial conditions which are, okay, which also satisfied. And it happens that just as the Q-Hermit polynomials, the continuous Kuelter-Circle polynomials for odd index are actually odd functions in x. So they can be expanded in power series of x with only odd exponents. And and those with even index are even functions. Okay. And of course, the constant terms are 0 for the odd functions. And for the even ones, okay, they're here, which can be easily, I think it's a special case, it's come from the Q-Kuma summation. One gets that because these are well poised. Yeah, maybe that can be explained. You see that this is actually well poised series. So there's a Q, which is, how does that work? Yeah, beta times, well, anyway, so it is a, yeah, well-poised series. And by specializing the e to the I theta, one can evaluate it by the Kuma summation. And that's exactly what is needed here. Anyway, here is also what Rogers needed, a nice property, a nice rule uh, for summing, for expanding the product of two continuous Kuelter-Circle polynomials in terms of continuous Kuelter-Circle polynomials again. And the coefficients are very nice. And it turns out that in one variable, x, the continuous Kuelter-Circle polynomials are the most general family of Q orthogonal polynomials that have this property that these linearization coefficients completely factorize. You you can extend this to several variables. So these would be then Macdonald polynomials. So if you have symmetric functions in x1 to xn, and you have q and t, instead of beta you have t, you have Macdonald polynomials, then you would have, let's say, a one-row Macdonald polynomial. And by the Puree formula, you would have, again, expansion in terms of Macdonald polynomials, and the coefficients factorized completely. So that is also a motivation was for me to study continuous Schlosser circle polynomials, because they are actually the one variable, or actually the two variable, actually the two variable special case of the Macdonald polynomials. The Macdonald polynomials in two variables, z1 and z2, where z1 times z2 equals 1, or if you take z1 equals z and z2 equals 1 over z, yeah, that's where you have the continuous Schlosser circle polynomials then. Okay, that's just a kind of motivation behind this. And now some further properties, which I all want to generalize. So here's the Askew-Wilson operator, which is also very useful in the study of the continuous Schlosser circle polynomials, which acts degree lowering on them. So this is how they're defined. If you have not seen this before, it's maybe too complicated to explain now. But this dq, so this is there's a Jackson's Q derivative, and this is a different type of Q derivative, which is symmetric, which acts on symmetric functions in Z and 1 over Z. And here's the degree lowering property. So if we have it act on Cn, it reduces the n by 1, but it also shifts beta by q. And we have some factor independent of x here. Okay, here's the orthogonality relation, the classical one. I mean, there's another one, which I will show you also, which I will need. But this is one for beta less than 1 in absolute value. I will need a more general one, which I will show you soon. This is the weight function. So the weight is q positive. Yeah, so for actually there are conditions on positivity. Actually, we will need actually q being a real number between 0 and 1 and other conditions. And I think beta less than 1 will be then the condition. But here, in this case, in the general case, so that this identity holds, beta can be a complex number and q can be a complex number. So in this generalized sense. But anyway, so what is remarkable here, we have Cm, Cn, integral from -1 to 1 on the real line. Of course, we can also view that as an integral on the unit circle by a substitution of parameters. But anyway, so this is now the real line version. And this is the weight. Okay. In the bilateral case, this weight will have more factors. So think of the one psi1 summation. It also, the Q product has much more factors, 4 times as many factors. And similarly, in the bilateral case, you will also have many more factors instead of this weight function here. And also here you will have more factors. Okay. You can multiply this by t1 to the n m and t2 to the n and sum over m and n. And then using, what was it, this relation here. So it's actually, this is equivalent to this integral evaluation, which was observed by Ismail. What is maybe not so nice here that this is a 2-phi-1 and not a closed form product. It's almost closed form, just contiguous to a closed form product. And it is possible actually to to use this uh, generating function instead, which is contiguous to the generating function I just showed you, to get closed form products of integrals. So there will be some, so here you see a beta t1, here you have a q times beta theta 2. So this is somehow contiguous, or here we have also a little difference here. So in some way, this is maybe nicer because you have closed form products on the right-hand side. And I believe this has not been maybe um, discovered before or written out before explicitly, but I may be wrong. But anyway, this is not the, I have more general things coming from from the bilateral theory, which extend these results even more. Okay, so actually I will need a more general uh, orthogonality relation. And maybe I just show you the nature here. So this is beta less than 1. But in doing analytic continuation, my beta I will give you an orthogonality relation, a more general one, where we'll say that this is analytic I will have a gamma in addition, not just a beta, but also a gamma. And then I will say that for gamma equals q, 1, q squared, q third, and so this is all, I will have different instances of the classical orthogonality relation. But, but unfortunately, in those cases, the beta will be then beta q to the minus s. And for large S, this will be larger than 1. So I actually need a version where this orthogonality relation holds for beta larger than S. And this is here. So this is the usual. So here, now beta, so I will have extra mass points. That is the solution. And so Q is still between 0 and 1. Now I take it as a real number for real orthogonality. Beta is now, let's say, greater than 1. And if I will have poles which are not in the unit. So if I think of the integral being a one like like Cauchy's integral formula on the unit circle, I will have poles now which are outside. So I have to expand my path of integration. So I have a detour, and then I will have a very small circle outside, corresponding to this poles created to the right of 1. So beta is greater than 1. And there will be extra points which I have to sum up. So extra residues. There will be all finitely many, yeah, depending on this. So I mentioned beta q to the s, but here it's beta q to the j, depending where this is greater than 1. Okay, so for those points, I have finitely many. So for given beta, uh, I take those for those j where beta q to the j is greater than 1, I have to have extra points. And that corrects the formula. So the right-hand side is again the same product, here the same integral, but I have additional mass points, which I have to add. That's quite interesting. And now I can define, now this will be used later. And what I'm doing now in the next, now we can forget this complicated looking formula. Maybe maybe I just explain the formula here that this is CMCN. I have CMCN, the same, but the xj, these are the mass points at these points. So that's where the poles appear, which are not in the unit circle, the additional ones, which I have to circumvent still. I have to, yeah, go around. And then the residues are computed here. Okay, they come from with the weight function and so on. Okay. Here's now the definition of the bilateral Kueltel circle functions. So similar to the 1 psi 1, where not only have the A in the top and also the B in the bottom, now we have the beta on top, and instead of the Q on the bottom, which makes the series truncate from below and from the top, we introduce the gamma. So we have Q gamma here, which if that is not a non-negative power of Q, this will be a true bilateral series here. And actually this is even analytic in gamma, which is useful because we can then put gamma is beta to the S and or minus S. There were different values and I think it's minus S. Beta, bet, beta to the S, sorry, beta Q to the S, yeah. And then we will get different instances of polynomials then. Yeah, okay. But anyway, so you understand now that these are 2 psi 2 series. They can be written in this form. This is now well poised. Beta times q to the 1 minus n over beta is q to the 1 minus n. Similarly, this factor times that is q to the 1 minus n. And we have some argument which depends on e to the I theta. There's also symmetry in e to the I theta and e to the minus I theta involved, which is one of Bailey's 2 psi 2 summations. There's also symmetry in replacing n by minus n. And at the same time, we would replace beta by 1 over gamma and gamma by 1 over beta and get an extra factor that can be easily got from this here. Okay, so what is interesting now, these are indexed not only by non-negative integers n, but by any integer n, also negative ones. This is now the generating function, which is a bilateral, I call it a bilateral generating function. Okay, I multiply by t to the n, just like in the 1 psi 1 summation, the power series variable. Now, so power series variable is t. And I can, because these are defined for any n, and I sum over all n. I have certain condition of convergence. And by two instances of the 1 psi 1 summation, this simplifies to closed form. So here I show you a proof, because every talk should have at least one proof. Here I give it in detail. So I sum over all n, then this is the sum over all k. The t to the n I write as k and n minus k, and you see that I can split k and n minus k everywhere. And where I have n minus k, I just shift n by n plus k. So this now splits in a sum depending only on k and one depending only on n. And both sums can be evaluated by 1 psi 1, by the 1 psi 1 summation. And that's how I get this closed form product. Okay. This is not just nice, this is also useful. I can immediately by multiplying t by q and looking at the difference and what I get and things like, I mean, I can immediately get a functional equation. And this is actually this recurrence relation, which is easily seen to extend the one for the continuous Kueltel circle polynomials. So it's again a three-term relation. We have some multiple of x here, then we have n plus 1 here. Here we have n minus 1. And if gamma is 1, we have the classical case. Only the initial conditions are not so nice anymore. And also, actually, this does not naturally stop with 0 or so. So before we had, sorry, so we had C0 being 1 and C minus 1 being 0. Of course, if gamma is 1, you see immediately this will be 0. And if gamma is 1 here, you see that this 2 psi 2, it reduces to a 2 phi 1 with just one term, the first term. But anyway, so this recurrence relation holds for all n. So we can just give two middle conditions, C0 and C minus 1. We could give any true values. And they determine now the sequence completely. Now we can, so it's interesting, they are not closed form, but okay. Are there values of x maybe for which they are closed form? And yes, it exists. Then we can use the Bailey's 3 psi 3 summations, special cases, where they, yeah, for certain x, where we have a complete factorization. Okay, they may not be very useful, these, but anyway, it just shows that for certain values of x, we do have factorization. Also, they are, okay, that I didn't mention. They are actually analytic in X, so they are not bilateral in X. So these functions, sorry, I'm back here. They're still analytic functions in X. As series over K, they are bilateral series, but as functions in X, they're analytic functions. They're not polynomials in X, but they're analytic in X. And here is, yes, and actually they're odd functions for odd indexed with constant term 0, of course. And for even functions, the constant term is now here. It's a closed form, which is can be evaluated by the Q-Kuma summation, by the bilateral extension. The Askew-Wilson operator acts nicely on them, also degree lowering. The beta is shifted by Q as before, but the gamma is not shifted. There are extensions of this, the Rodriguez formulas, which I'm not showing you on my slides today, but they are in my paper. So there are more general formulas for, yeah, in any way. Okay, so now we come to the main result, orthogonality. I will need, to construct orthogonality, I will need the more general orthogonality relation of the continuous Schlosser polynomials, which involve the mass points. That is where so beta, I can assume beta less than 1, but I will then have, I think, beta q to the minus s. Yes, okay. So I will have, so gamma, so my gamma will be, the gamma, I can take q to the 1, q to the 2, q to the 3, q to the 4, and so on. And that will create different instances of the q ultraspherical polynomials, where beta is replaced by beta q to the minus s then. So when gamma is q to the s. So at some moment, the beta will be larger than 1. And then I will have these mass points. And so this is now just a symmetrized product, which I defined to make the formulas more compact. So xa is just this nice factor. Of course, this will be then some function depending on beta and e to the I theta, but anyway, here we have plus xa, here we have minus xa. And remember that the uh, continuous quadratic functions, they preserve for their index the parity. That means they're even functions for even index, odd functions for odd index. So if m and n have different parity, this minus here will create here a minus in the end. And this will be then 0. Okay, but anyway. And now what is also interesting, although the mass point formula has finitely many terms, in the analytic continued case, I will have an infinite series. So if gamma, maybe forget the second version here, the M2, just look at the M1 and think of gamma being q to the s, let's say, s being either 1, 2, 3, and so on. In that case, this is a finite series because we have q to the minus s then here. This starts with 1 here, not with 0. So with q to the minus 1, it will be already just a closed form. This will be just one term. And everything will then... So otherwise, we'll have more terms. So we'll have a series here. So we will have these additional series. So these series in addition to the integrals. So they will come from the mass point. The analytic continuation of the mass point formula will involve this infinite series. On the product side, instead of having just simple factors, we have now infinite products. And they come from the analytic continuation as you want. So for gamma equals 1, they reduce to just a few factors, and so these will be the squared norms. So this is the H1. The H2 is just by symmetry. If we replace n by minus n and beta and gamma by 1 over gamma and 1 over beta, we get then essentially the second form. See, beta replaced by 1 over gamma, 1 over beta, yeah, and gamma by 1 over beta. Yeah, so these are just two ways. So if one has one orthogonality relation, one gets another essentially for free by symmetry in the bilateral case. And then we'll have a third one. But anyway, so now I told you already that we will have more factors also for the weight, for the measure, similar that the 1/1 summation has many factors on the right-hand side for the Q product. Now we have many more factors. And again, if gamma is 1, this will reduce here. This will just it will cancel. But otherwise, this is analytic in gamma, and we will have extra factors here in the weight. Also, this is analytic in gamma, if you can see here. This not, because we replaced beta by 1 over gamma. So this is, yeah. But here, in the first case we have. The second case is again by symmetry, by replacing beta by 1 over gamma and so on. So just think of this being now the new weight function. Okay, and this is now the main result, the orthogonality for the bilateral quadratic functions. Again, just think of the first formula. The second it comes from symmetry in a way. So there's a second form, but anyway, so we have certain conditions on the parameters, and this relation. So we have the pair Cm and Cn, then the weight function with the many factors depending. I'll just go back for short. depending on beta and gamma. And also it looks very much the same as before. And also the H1, the squared normal variation looks more blown up. It's many factors. And then there's a correction series uh, for the integral, which comes from the mass point formula, but now by the analytic continuation of it. That is here. So this is the integral. Then we have a series. So we have, let's say, a second term, but this is not an integral, but just a series. So it's a discrete integral, one could say. And this is now the analytic continuation of the squared norm, m and n. And m and n can be arbitrary integers. So this has been checked by computer uh, because it's really, actually it's not even so easy to check it because the integrals, yeah, they have, if one is closed, if one takes the path of integration and was close to the poles, the error gets very strong. So one has uh, to be very clever, even with checking numerically such integrals on the computer. But there are certain techniques which achieve that. Okay, so having this first formula, the second one comes out by symmetry by replacing m and n by minus m and minus n and beta and gamma by 1 over gamma and 1 over beta. And actually, there's a third relation, which I'm not showing you here, by combining these two and using identities for theta functions by the Weierstrass addition formula for theta function. So one can take a nice linear combination of these two integrals. So this is again the Cm and Cn, so nothing changed, but here's some Q product, here's another Q product. There are theta functions involved here. So this is beta e to the I theta. Here is Q over these things. Just this is not a theta function, but anyway, so one can multiply factors so that a linear combination of these two simplifies again to a Q product. And interestingly, the same linear combination will make these two factorize. So this product times H1 times that missing product times H2 will make this again factorize. So that is nice. So one has then another formula where I call it then W4, not W3, because it has then, instead of two factors, 1, 2, we'll have actually four factors, 1, 2, 3, 4. So it has even more factors, and it's quite interesting. Yeah. Here, I'm already just giving you an outlook. So I have I explained how I obtained another full orthogonality relation. I also have shifted orthogonality relations, which originally I had before I had the full orthogonality, where I then had to realize that I needed this mass point formula for the full orthogonality, but naively, without having that, I was only to obtain what I called shifted orthogonality, but I still have that in my paper. In it, so one has bilateral generating functions and corresponding integral evaluations by summing both sides of the orthogonality relation in the bilateral case and evaluating it. One has very huge integral evaluations, which also appear to be new, but there is this correction series in addition. I look at asymptotic expansions for large n and large minus n, Rodriguez type formula. So that means essentially the action of the Esky-Wilson operator on the weight function itself, which is a kernel of the family of bilateral continuous group of circle functions, and so there's nice formulas there too. Then linearization formula, which extend those of by Rogers, and then even for there's also mixed integral. I mean, for mixed continuous group of circle polynomials. So I have beta. So here I have beta and gamma. So I can have, let's say, beta gamma, and here I can have alpha delta, and uh, and have similar evaluations, because of course they can be expanded in terms of the Cn again, those other ones, and yeah. So there's a nice closed form also. Yeah. And then there is work. So this is work I did already. And then there's work which one I would like to do next, to look at bilateral extensions of other Q, orthogonal polynomials. In particular, it would be interesting to study the most general family, which is on the top of the ASCII scheme, to look at the ASCII-Wilson polynomials and see if they can be bilateralized. Maybe the 6 psi 6 summation will be involved somehow there, or some 8 psi 8 summations, I don't know, or transformations. Okay, at least it should be studied, even if to see how far one can go. And of course, multilateral extensions. So, because the Q circle polynomials, they're special cases of the McDonald polynomials. Can the McDonald polynomials be extended to multilateral series so that they are still orthogonal? I hope I caught your interest. So full details are in my uh, preprint, which in the second version of that, which 1 year ago I had much less results, and in June or May, maybe May or June, I just gave the second version, and it contains all these details. So thank you very much for your attention.
Thank you, Michael. Any questions?
Yes, sir.
Go ahead, Srinivas.
Yeah. Hello, sir. Thanks for
Hello.
the excellent talk. Yeah.
Mhm.
Yeah, Professor Michael Schlosser. I read your paper from ARXAV, sir, the version 2.
Yes, okay, good.
And yeah, it is a very interesting paper. Um, okay. And I prepared some notes, sir, on your paper.
Yeah.
Sir, may I ask you clarification about the mass aggregate? M
Yes.
subscript of M comma N
Yeah.
1 in the theorem 7.2a
7 point. Okay.
2a. Yes, sir.
Yes. I mean, is it
7.2a.
it's essentially it's what I have here,
Yes, sir.
or is
Yes,
it?
sir. Yes, sir.
Yeah.
Yes, sir.
Okay.
Yes, sir. I may be misunderstanding and intended to counter a continuation convention,
Yeah.
but I found that found some technical error, I think. For
Good.
example, sir, but it seems that summing over every r greater than or equal to 1 can include points that have not crossed a unit circle counter.
Yes. That could be.
Uh,
Maybe I need.
Actually, this is my notes. Maybe.
Yes. You're
Sorry for
right.
my bad
I
handwriting.
might have. I might have. I might have.
I found a counter example, sir.
Okay. So maybe I need to assume that beta is greater than q, something like that. That beta should be between q and 1.
Actually, if we take q is equal to 1 by 5, this is my
Yeah.
counter example, and beta
Okay.
is equal to 1 by 10, and gamma is equal to q, m is equal to n is equal to 0. Here
Yeah.
s is equal to 1, And the shifted Rogers parameter is alpha is equal to beta into q power minus 1 is equal to half. Since mod alpha less than 1, the corresponding ordinary continuous Q ultraspherical orthogonality relation is mass free.
Yes. Okay. I think you might be right. I think I realized that myself at some point, that, and I had that and then I might have. So the paper is not published yet, and it's being refereed at the moment. So I can easily make changes still and correct things. And I believe that I need that beta is between Q and 1.
Yes,
Because
sir.
that explains why in the beginning so if beta is then Q to the minus S, yeah, it will be if S is 0, then it's still less than 1. Then I have no mass points.
Yes, sir. Yes, sir.
But if I multiply by Q to the minus S, yeah, by Q to the minus 1, it will be immediately in the first step. So there will be for each term, for each S, there will be 1 mass point extra. And I think
Yes, sir.
that's,
Yes, sir.
yeah. So
Exactly.
maybe keep that in mind. Otherwise, so maybe it's easy if you then contact me by email
Yeah, definitely, sir.
directly.
I will send this counter example and my argument through
Yes.
email. And
Yeah.
also, sir, proposition 6.2.
Yeah. Okay. So in any way, so here it might be that I also need. It might be that these two actually have separate conditions. So I need beta less Q less than beta less than 1 and yeah, okay, and so on. So what is your other remark?
Proposition 6.2, sir, uses an integral outside every valid starting domain.
Okay, so for that, I would need to.
I think there is a small correction in the proof.
Okay. Can
Okay.
I
For
interrupt here?
prepositions.
Yeah, Srinivas, can I interrupt here?
Yes, sir.
Okay. Is it okay if you just write directly to Michael
Definitely, sir.
and
Maybe
point out, and then he can look at it in length and then maybe incorporate in his next version.
yes.
That be okay?
Yes, sir. Sir,
Okay.
one important question I have, an important question.
Yeah.
How are the mass points selected?
They are. That is pretty clear. Wait a moment. I just wanted to. Is it here?
I'm a
Yeah.
little
The
bit
mass
confused,
points.
sir.
Yeah.
Yes, sir.
So that. Okay. So I have. Let's say the condition Q less than beta less than 1. Then I will have no mass points, but in the but for gamma equals Q to the S, yeah, what I have is I have an instance of Cn where beta is replaced by beta Q to the minus S, yeah. So that means I have this formula then, that beta Q to the I think minus S will then be positive for larger S. So it depends on how large the S is. And then I will have mass points, yeah, for each.
Okay.
And actually, I can exactly say how many, namely S many terms. So I will, yes. I think that's, so I think there will be no term then for, yeah. So for each, yeah. So it's quite exact. It's exact then, yeah.
Okay. Thank you.
I think we can have a continued fraction representation also, sir.
That might be, but yeah, I have not.
Yes, sir. I will send you my notes, sir. I will send you my
Okay, yeah,
notes on
well,
that.
interesting,
Definitely,
yeah.
sir.
So,
Yeah.
and
Thank you so
yeah,
much.
so I'm looking forward to communicate with you and
Definitely,
yeah,
sir.
yeah.
Any other questions or comments? Okay, I just want to make a comment before we close that, if from Favard's theorem, we know that there is a absolutely continuous component to the orthogonality as well as a discrete component. And the purely analytic methods don't really give the discrete component. They usually they're able to calculate the absolutely continuous component. So what is nice about your method is that somehow you have got both of them and you've knocked it off. And this is something which is a very subtle point, that there is always both of these are available. And typically there are theorems which say that if this happens, then there is a discrete component only, or there is no discrete component and things like that. So we'll try to get it. So this is a very explicit, it seems like a very explicit approach solves this whole problem of giving both the components at one time. So that is very nice. So if there are no further questions, I would like to stop the talk. Okay,
Yes, I
Abdul
will
Hafiz
stop the
has a
share.
problem. Abdul
Okay.
Hafiz has a question. How did you get the weight function to show the orthogonality?
Okay. So I just did analytic continuation. So it's similar to the one psi one, which one does by an analytic continuation. So if one has the one psi, if one has the Q binomial theorem, one has it start not with zeros, but writes it as a series from minus, let's say, s to infinity and so on. And then one wants to have it, this q to the s one replaced by the gamma, and wants to write everything as an analytic function gamma. So that essentially one is writing many products become quotients of products of infinite products. Yeah. And the weight function, if I look at the weight function, maybe you're not seeing my weight function. I have to share again.
Yeah.
But I think it would be that one. Yes. Yes. So if I go again to the weight function, I think here you see that maybe you don't see it, but yeah. I mean, of course, what you see if gamma is 1, that it reduces to the weight function of before. And I think if gamma is it's not that gamma is, yes, yeah, but then also the beta has to be replaced by beta q to the something. Okay, yeah, and these are then some okay, so for gamma being some q to something, this quotient will reduce to a to a finite number of factors. But if in addition beta is shifted by q, then because this is a data function, it's similar to the same data function up to some additional factors. Yeah, so this is involved. Yeah, I mean, it's a creative process, and one should probably do it by hand to see why one, yeah.
All right.